Going back to the last lecture, we looked at validities, and the last example of validities were the so-called quantifier validities. There's more quantifier validities, and one intuitively derives as follows. So suppose that for all x, psi of x holds in a structure M. Well, if that's the case, then psi of x should hold in M intuitively with whatever we plug in for x. Right? So if that's true, then this implication should be a validity, right? That because if this holds in a structure, then this psi of whatever should also hold in a structure, so this implication should be a validity. However, of course, this is not a formal expression at all. So to make this formal, we need to define substitution into formulas, because this whatever here should be then be formally defined in terms of substitute something for x. However, there's a few pitfalls, and if we are not careful, substitution may affect semantics significantly. So for example, take a look at this formula. Psi is for all x1, x1 is equal to x2. Now we substitute x1 for x2. Well, that would give us the formula psi prime, which is for all x1, x1 is equal to x1. But these two formulas have a very different truth behavior. Right? This latter formula here holds in any structure because it's always true that x1 is equal to x1, no matter what x1 is. But this formula here, right, for all x1, x1 is equal to x2, holds only in structures that have exactly one element, because then everything would be equal to that interpretation of the second element. The problem that we just saw, of course, can be summed up as follows. We simply cannot substitute terms with a variable x into a formula where x would become bound by a quantifier. So where we would have, for example, for all x, x equals y, right? And now we want to plug something in for y, and if that something we want to plug in is x, then we get into trouble, because x suddenly is in the realm of that quantifier. There's two possible solutions to this when defining substitution. One, you could, from the beginning, allow substitution only into formulas where no such conflict arises. Or the other solution would be, since any formula has only finitely many variables, we can just find a variable that voids that conflict, and we change the variables accordingly. We will follow here the second approach. It will make the actual definition of substitution a little bit more involved, but the proof of the substitution theorem will be easier. As usual, when we want to define something for formulas, we first have to do it for terms. For terms, however, everything is pretty straightforward because we don't have quantifiers around yet that we would have to be careful with. So let t be a term with variables x1 up to xn and t1 up to tn be terms. Now we define the term that we get if we simultaneously substitute ti for each occurrence of xi and t. So this is the notation for this. Right? And important here is just the simultaneous procedure. So you just take each ti and plug it in for each occurrence of xi and t. So you don't do it one after the other, you just really do it simultaneously. So for example, here we have t, x1 x plus x2, t1 is x1 times x2, t2 is x1 plus x2, so actually the original t, but there's nothing to prevent us from doing that. And then this term ti for xi would be just taking this right? And this is our original term. Then we take t1 and plug it in for x1, right? And then we would take t2, this one, and plug it in for x2. And hence we get this and this, right? So keep in mind, we're really doing simultaneous substitution, so nothing of the sort. We first substitute at each xi's, right? And then see what we have, and then we take the next j, and possibly then substituting occurrences that have been introduced while doing this substitution procedure for xi. And so nothing of that happens, really just doing it simultaneously for all. You should take a few moments to verify that this is really a term again. It's not hard to see, and as usual you can proceed, for example, by induction on the term height. And you should also verify the following, right? If you have a term that is obtained by applying a function symbol to a bunch of terms, then if you want to substitute a term for x, right, so or a sequence of terms for a sequence of variables x, that is the same as first substituting in each of the terms si's, right, and then applying f to it. Again, take a few moments to verify that. Now we're able to state the substitution lemma for terms. Let's let alpha be an M assignment, and assume we have variables xi, and we have values in our domain a1 up to an. So we can define a new assignment, and this new assignment, alpha sub this long term here, essentially just means whenever we have an xi, we evaluate that to ai, right? And otherwise we leave alpha untouched, right? So whenever your v is one of the xi's, you map this assignment to ai, otherwise you just leave it untouched. Okay, so now let's assume that x1 up to xn be variables, s1 up to sn are terms, and alpha is an M assignment. If we let a sub I be the value that we get if we evaluate the term s sub I in M with respect to the assignment alpha, then the value that we get if we evaluate the term that we get if we substitute s for x is the same value that we get if we evaluate the original term t in M, but we change the evaluation or the assignment from alpha to alpha with this modified assignment function up here. So again, what this says is that it doesn't matter whether you first substitute and then evaluate according to the original alpha, or first evaluate the terms that you will later substitute, right, and then evaluate with this modified alpha, where you essentially change the value to the values that you obtain if you evaluate the substitution terms first, and then evaluate the original term over that assignment. That gives you the same value. Now we can move on to substitution for formulas. Here in this case we define it inductively because there is this case of the quantifier that we have to be careful with, so that's why we have to do it inductively here. All cases except for the quantifier case in the definition of a formula are unproblematic. So for example, if we have an atomic formula that is just term t equals term t prime, and we want to substitute s for x, well, that's just the term t substituted, s substituted for x, equals term t prime s substituted for x. Similarly for relations, and then the inductive cases, right? For negation, straightforward, we just substitute everything in the formula that we negate and then put the negation symbol in front. And similarly, if we have a conjunction, we first substitute in the formulas that make up the conjunction and then form the AND of the two. So now comes the more complicated quantifier case. So assume now we have a formula of the form there exists x psi. So what we first do is we collect all variables among the variables that occur in this formula. We collect those variables that occur free in this formula. Let's say those are x sub I1 up to x sub ik. And these are the potential troublemakers, right? Because they occur free in this formula, and we're not supposed to substitute anything for them that would potentially make a variable bound by this quantifier exists x. Okay, so now we distinguish two cases. The first one is if x has no occurrence in any of those s sub i's, right, that we want to substitute for the xi's here, or rather the xij's here, well, that's good, right? Then no danger. We can just substitute. Well, in this case, our substituted formula, right, exists x, and then we take the formula of psi and do our substitution there. However, we only do we substitute the free variables, right? If the variable is already bound in here by some quantifier, we don't want to substitute that because they're already bound. Okay, so substitute as usual, but only the free variables. If x has some occurrence in any of the Sij's here, well, that's the bad case, right? Then we have to be careful, because then we run into danger if we now substitute one of, let's say, s sub I sub 1 into psi here, then x and x occurs in this, then we would substitute into the range of this quantifier here. Well, in that case, we actually now proceed with renaming the quantified variable. And for this, we let u be the variable with the least index. Remember, we assumed that our variable set v was given as vn's, where n is in omega, or all right, and that means our variables are enumerated, and we just pick the one, right? Since any formula can have at most finitely many variables, there has to be at least one that does not occur in any of the formulas that are under consideration here, right? So let that variable be u. And now we do our substitution almost like this one above, except that we substitute in the si's for the xi's, right? Restricted to the free variables, of course. But we also rename u to x, and then of course we also have to rename. We have to substitute every occurrence of x by u, right, in the rest of the formula. This is why this extra bit here in this substitution occurs. So finally, we can state the substitution lemma for formulas. And as you will see, it's actually not that different from terms, except that now we're interested in whether a formula holds in a structure under a certain assignment or not. So essentially, this is similar to the term case, namely, it just says, the lemma just says that it doesn't really matter if we first substitute and then evaluate, right? Or if we first evaluate the terms that we substitute, change our assignment currently, and then evaluate phi inside M with respect to that changed assignment. So in other words, the lemma says if we let AI be the value that we obtain if we evaluate the term Si in M under the assignment alpha, then the substituted formula holds on the original assignment in M if and only if the original formula holds under the changed assignment. The proof, as you may guess, works by induction on the height of phi. The non-critical cases are really straightforward because there's really not much to do, because the definition of substitution in these cases is so simple. And for the critical case of existential quantification, you distinguish the two cases, paralleling the definition, right? Because you say whether or not the variable over which you quantify occurs in one of the terms that you substitute. As a first application of substitution, we return to validities. So taking up that example from the very beginning, namely that if you have a formula that for which for all x phi for that formula holds, then it should be true that phi holds with whatever you plug in for x. Now we can make this precise. And here's the proposition. For any formula phi, for any term t, and any variable x, the formulas for all x phi implies phi. And now we have this whatever is just plugging in or substituting t for x. That's a validity. And similarly, if phi is true, if we plug in or substitute t for x, then it holds that there exists an x phi of x. So here you can think of, there's a value for which phi holds, represented by t, right? Then that is a witness for the existential statement. So take a few moments to prove these. It will be a good exercise not only to see if you understood the substitution lemma, but also if you understood the definition of the satisfaction relation for quantifiers.